Welcome, dear students. Today we will discuss adherent points, which also called cluster points or contact point, and isolated points. So first of all, we memorize the definition on limiting points. A real number x naught is said to be a limiting point of S, which is also subset of R, if there exists an open interval or every neighborhood of x naught, that is x naught minus epsilon to x naught plus epsilon, contains at least one point of S other than x naught. That is the mathematical tool source for limiting point, for limit points, the tools was x naught minus epsilon to x naught plus epsilon intersect with the set other than x naught should be non-empty. If a real number x naught satisfy this condition, then x0 is said to be limit point of the set S. Now we are going to define what is adherent point of a set. So we take the definition of adherent point of set. Definition of adherent point. Adherent point of a set. Let S be a subset of R. A real number x naught is said to be an adherent point of S if there is if every neighborhood of x naught contains at least one point of S. That is, the mathematical tools will be like this, except this expression. If x naught minus epsilon to x naught plus epsilon intersect with the set, then which set will be or should be non-empty set. If a real number satisfy these characteristics or tools, then we can say that x0 is an adherent point from the set S for every epsilon greater than 0. So for adherent point, we have the tools x naught minus epsilon to x naught plus epsilon, which intersect with S, and this set should be non-empty set. Now we are going to define isolated point. A point x naught which belongs to the set S, where S is a subset of R. A point x naught belongs to S is said to be an isolated point of S if it is not a limit point of S. one thing is here very important. Isolated point must belong to the set of the respective set. Or in another word, we can say that, in another words, uh, a point x naught belongs to S is said to be an isolated point of S which is subset of R if there exists a neighborhood. Follow this. If there exists a neighborhood x naught minus epsilon 2 x naught plus epsilon which contains no point of S other than itself, other than x naught, and that is if x naught minus epsilon to x naught plus epsilon intersect with the set which is a singleton set, and this set contains only the respective point x0. If this intersection is x0 which is itself, then it is said to be an isolated point of S. So it is very important. Isolated point must be lie on respective set. For isolated points, we have tools x naught minus epsilon to x naught plus epsilon intersect with S which contains a number x naught. In this COVID-19 situation, we are very much familiar with the word isolation or isolated person. We sometimes do not know the properties of isolation or isolated person. When a person can be said an isolated person. First of all, if we call a person an isolated person of my family, first of all, he or she belongs to my family. And then if we make a neighborhood around him or her, then it does not contain any member other than himself or herself. That is, no members are the neighborhood of this person, and also this person cannot be a neighborhood of other person of this family. Then he will or she will be called isolated person of this family. And of course, he or she will not be an isolated person of other family. However, we are going to the example on adherent point and isolated point. First of all, we take an example 1, which is a finite set. Suppose A equals 1, 2, 3. Now, first of all, we will find out if exists limiting point, adherent point, and isolated point of this set. If we take a number from this set for isolated point must lie on respective set. So let x naught equal to 1. And now if we make an interval or neighborhood around 1, we have got 1 minus epsilon to 1 plus epsilon. Now if we intersect with the set S, then we can get only one number which is 1. The intersection of this interval around 1 and S will result only singleton set 1, which is 1, and 1 is included in this set. So As per definition of isolated points, we can say that one is an isolated point of this set. So one is x0 equal to 1 is an isolated point of S. Similarly, if we check the other points 2 and 3, we will see that 2 and 3 will also be an isolated point of S. And any real number outside of this set cannot be isolated point of this set. Now we check the adherent point of this set. Again, if we take x not equal to 1, then this operation must non-empty. We see here this operation results 1, which is non-empty. Since it is non-empty, then we can say that 1 is an adherent point of S. Here also x not equal to 1 is an adherent point of S. So we can say here easily, if a set have isolated point, then actually it is an adherent point. If a set have isolated point, then it is an adherent point. Now we check whether 1 or 2 or 3 will be limit point of this set, or this set has limit point or not. We know that a finite set has no limit point. So this set has no limit point. S has no limit point of S. So we can say that every number of this set is isolated point, also adherent point. But these numbers are not a limiting point of this set. The result is, if x0 is an isolated point, then it is an adherent point. So x0 is isolated point, then it implies an adherent point, but it does not imply that limit point. This is very important relation. It will help us in future discussion. Follow just here is an important observation. If a set has isolated point, then all of its elements will be an isolated point of this set. So we can say that the set of isolated point of a set is itself. That is, isolated point, the set of isolated point of S equal to S. The set of isolated point, the set of isolated point of S equal to S. If a set containing all of its points are isolated point, such type of set is called discrete set. If the set of isolated point of S equal to itself, then S is said to be discrete set. So S is said to be a discrete set. So we can say that the above mentioned set, finite set 1, 2, 3, is a discrete set. Discrete set will also be an infinite set. Our second example is example number 2, S equal to n, a closed interval 1 to 4. Now we will also find out the all respective point of this set. First of all, we take a number from this set and of its integral point, let x not equal 2. Then if we check these tools, so what we get is here 2 minus epsilon, 2 plus epsilon. If we intersect with S, as we have got a non-empty set. Actually, this interval contains infinitely many points of this set. So it is non-empty set. Since it is non-empty set, so we can say that 2 is an adherent point of set. Also, if we check these tools, that is, and 2 minus epsilon 2, 2 plus epsilon intersect with S minus 2 itself, then it will also be a non-empty set. So we can say that 2 is a limiting point of this set. But this set cannot be, this set cannot contain any point along with 2. That is, this operation for isolated point, it contains infinite number of points. So this does not contain only one point x. So we can say that 2 is not an isolated point of this set. And similarly, every point can be treated as limit point of this set as well as adherent point of this set. If we check at boundary point, so we can also see that 4 is a limit point of this set and adherent point of this set. So 2 is an adherent point of this set, also limit point of this set, but not isolated point of this set. Here, every point of this set will be limit point and also adherent point. So we can say that adherent point is every point of a set. That is, every point of a set S is an adherent point of S. But for every set, every point of S will not be a limiting point of this set. We will see such type of example in future. So here we get another relation. X naught is limit point, which implies that it is a adherent point, but it is not an isolated point. If a point is limit point, it implies that it will be adherent point, but it does not imply that it will be an isolated point. Now we take another example. Let S equal an open interval 1 to 3. Now, if we check all these points of this set, similar to the previous set, every point in between 1 and 3 will be limiting point of the set and adherent point of the set, but no point in between these 2 points will be an isolated point of this set. Now, if we take a point close to boundary, let x is not equal 3. So we see that these operations will be 3 minus epsilon to 3 plus epsilon. If we intersect with S, then we have got a non-empty set. Since we have got a non-empty set, then it is called a limit point of this set. Also, it is called an adherent point of this set. Limit point of this set, actually, if we discard from here x naught, so we have got infinite number of real number which belong to this set, and that is why it is called, and 3 is called a limit point of this set. But this intersection contains infinite number of sets, so this intersection does not contain only one point x naught. So we can say that 3 is not a neighborhood, 3 is not an isolated point of this set. So we have got similar result. It is a limit point which indicates that it is an adherent point, but it does not indicate that it is an isolated point. Here, one thing is very most important. All the point of a set will be an adherent point. Also, adherent point can be situated at outside of this set. We can take another example. Suppose Example 4, let S equal 1 by n, where n belongs to set of natural number. We saw that this set was 1, half, 1/3, and 1/4, and so on. So we saw that limit point of this set is 0. Limit point of S equal to 0. This 0 is also an adherent point of this set. If we check this operation, then we have got 0 minus epsilon to 0 plus epsilon, which intersect with S. We have got a non-empty set. Since it is a non-empty set, it contains many numbers of this set. That is why 0 is called limit point as well as it is an adherent point. Here, one thing is very most important. Limit point only 1, 0, but all these elements will be treated as adherent point as well as isolated point as per definition. 1, half, 1/3, all these numbers will be adherent point of this set and also isolated point of this set. If this set have isolated point, actually these points are adherent point. So we can say that adherent point can be lie on this set or outside this set to the boundary or exterior point of a set. This is very much important criteria of adherent point. So here, if x is equal to 0, this will be a limit point of this set. Limit point of this set, which implies that it is also adherent point of this set. But it does not imply that it is isolated point of this set. But for this element, every element is isolated point of this set. So if we remark this set by x naught, so we can say that x naught is isolated point, which are also adherent point, but they are not limiting point. Actually, which is described on this. From these two examples, we can say that the set of all adherent points of a set. The set of all adherent points of a set, actually it is itself and the union of limiting point of a set. So the set of all adherent points of a set is said to be closure of S. The set of all adherent point of a set S is said to be closure of the set S, and it is denoted by S bar, and S bar contains completely S, and it contains other extra points. So we can say that the set of all adherent points or the set of the closure of the set S is S bar, which contains S. So the set of all adherent points contains the original set S. Therefore, S is a subset of all S bar. This is a very important criteria. That is, adherence means the set of all adherent points. Adherence of S is subset of S bar, which is here S is subset of adherence of S. We say here again, adherence of S means the set of all adherent point of a set. Since all adherent point of a set is denoted by S bar, then S is subset of S bar. Dear students, now you are advised to keep your deep concentration on this discussion or on this section. Actually, after discussing this section, we will be able to distinguish among adherent point, isolated point, and limiting points. from here we can say that isolated point, which is isolated point, this also adherent point. Which is limit point, this also limit point, this also which indicates adherent point. So we can say that if a point is an isolated point of a set, this point will also be an adherent point of this set. If a point of a set is limit point of a set, or if a real number is a limit point of a set, then this real number will also be adherent point of this set. So we can say that if a real number is adherent point of a set, this point need not to be an isolated point of this set. We can say from here. Also, if a real number is an adherent point of a set, so this point need not to be a limit point of this set. We can say that from here. So every isolated point is an adherent point. Every limit point is an adherent point. But the converse is not always true. So from here, we can say that actually adherent points are two types. Adherent points are two types. One type is isolated point, and the other type is limiting point. Limiting points. Adherent points actually divided into two class. One is isolated point, and the other is limiting points. Actually, these are the distinguish among adherent point, isolated point, and limiting point. They are very much close, but there are some specific distinction or specific difference among them. We know that set of isolated point is itself. That is, every member of the set is an isolated point of the set if it there exists an isolated point. So the set of isolated point can be denoted by itself S. And we know that set of all limiting points can be described by S prime, derived set of S. So we can say that the set of all adherent points of a set, that is closure of a point, closure to all adherence of a set that is S closure. And adherence of a set, or the set of all adherent points of a set, is denoted by S bar, which is the combination of set of isolated points and the set of limiting points, which is very most important theorem or a tools for limiting points, isolated points, and adherent points. And the closure set of S equal to S union S derived set. Here it is also called or closure of S, that is S bar equal S union S derived set. Here it is an evidence that every element of S is either an isolated point or a limiting point. It is also very most important theorem or properties or characteristics of this set. It is evident that each element of a set S is either an isolated point of S or a limiting point of set S. I again declare this. It is an evidence that each element of a set S is either an isolated point of S or a limiting point of S. So, dear students, this was my today's effort to discuss with you about adherent point, isolated point, and average limiting points. Thank you, everyone.